Hi, welcome back to the second part of the lecture. Today I'm going to discuss some of the methods of the proof of the main theorem. Then I'm going to show that this second bound is indeed best possible. And finally I'll say some things that we do know to say about co-compact lattices. So let me remind you of the main theorem. We show that if H is a simple Lie group of high rank, then the minimal number of generators of every non-uniform lattice gamma in H is bounded logarithmically in the volume of H mod gamma. And if in addition H satisfies some number theoretic conditions, then this bound can be improved to log of the volume over log of the volume. So first, we believe that the second bound should be true for every Lie group. And the difficulty arises from some number theoretic conjecture about the class groups of number fields. In fact, we show that if this better bound can be shown for every Lie group, then these number theoretic conjectures are true. So this was a classical result of Gauss, which gives a very precise description of the order of the two torsion of the class group of some number fields. But other p torsion in these class groups are completely unknown. But still, it is widely believed that these conjectures are true. And so this second bound should be true for every Lie group. Now the second remark is that this bound is best possible. And I'd like to show you a bit of why this is true, because it reveals somehow the approach to these types of questions. So take for example the non-uniform lattice SL3Z. So this is a lattice in SL3R with a non-compact quotient. And now we are going to look at the mth principal congruent subgroups. So these are a family of finite index subgroups, which are very important, which are given by the kernel of the map, which takes each entry of the matrix modulo m. So gamma m is the kernel of this map, and so the quotient is isomorphic to SL3 with coefficients in the range z modulo mz. So this is a finite index subgroup, and the index is bounded, for example, by m to the 8th, since this is the dimension of SL3, and thus this is also a lattice in SL3R. And now SL3 with coefficients in z modulo mz is isomorphic to the product of SL3 fp for every p which divides m. But now each of the copies of SL3 fp contains an element of order 2, and so SL3 z modulo mz contains a subgroup which is isomorphic to f2 to the L, where f2 is the field with two elements, and L is the number of primes dividing m. If we pull back this subgroup to SL3Z, we get a subgroup gamma tag, which sits between gamma m and SL3Z, and has index at most m to the 8th, and it projects onto f2 to the L, which has rank L. So we would like to take m, which has many different prime divisors. For example, the product of the first x primes. And if you work out the details of what is the size of the product of the first x primes with respect to the index, which is m to the 8th, you will get that this specific subgroup has rank which is at least log v over log v, since its covolume is proportional to m. And we use this idea to show this for every lattice, and in fact for all finitely generated linear groups over arbitrary fields. So this shows that this second bound cannot be improved. Now let me say what we do know for co-compact lattices. So for these lattices, we are missing a crucial ingredient, which I will discuss later. However, our second result is that we cannot expect such a good bound for these lattices. So here is the second theorem. If H is a simple Lie group of higher rank, then there is a constant and a sequence of uniform lattices gamma I such that the number of generators of gamma I is at least logarithmic in the covolume of the lattice. Which in particular means that the second bound cannot be true for all co-compact lattices. And a nice feature of the proof is that we cannot look at subgroups of the same co-compact lattices. Each of the different gamma i's lies in a different maximal lattice. And this is the only way to generate these examples. This shows another distinction between co-compact and non-co-compact lattices, which comes from the fact that uniform lattices are defined over number fields of bounded degree. So what do we mean by that? Let H be a simple Lie group and G an algebraic connected simple group defined over a number field K with an epimorphism phi from G to H whose kernel is compact. Then the image of G of O, where O is the ring of integers of K, and groups which are commensurable with it are called arithmetic. So if you didn't understand that, that's okay, but you can think of things like SL3Z or SL3Z square root of 2. So these are the types of lattices that we deal with, and in fact, in higher rank, these are the only lattices that appear. So Margulis showed that all irreducible lattices in higher rank are arithmetic, which is called the Margulis arithmeticity theorem. And the degree of the field which defines the lattice is unbounded for co-compact lattices, but it is bounded for non-co-compact lattices. The first ingredient in the proof, and really the main thing which is missing for co-compact lattices, the following result of Sharma and Venkatramanna from 2005. They show that every high-rank non-uniform arithmetic group gamma has a subgroup of finite index which is generated by at most 3 elements. So, given gamma a non-uniform lattice, we know that there exists a finite index subgroup, say delta, such that delta can be generated by at most 3 elements. So we have that the number of generators of gamma is bounded by the number of generators of gamma mod delta plus 3. So this is because if you can generate the quotient and the subgroup, then you can generate the entire group. But gamma mod delta is some finite quotient of gamma, which we do not know exactly which one it is. So it would be enough to bound the number of generators of all finite quotients of gamma. But wait, that sounds pretty hard. But for that, we have what's called the profinite completion of a group. So let me briefly define it. So a profinite group is a topological group which is the inverse limit of finite groups. It is a compact Hausdorff totally disconnected group. From that, there is a natural construction which is called the profinite completion of a group gamma. It is given by looking at all the finite index subgroups of gamma and taking the inverse limit of the quotients, which is partially ordered by inclusion. So gamma hat, the profinite completion of gamma, is equal to the inverse limit of gamma mod n, where n is a finite index normal subgroup in gamma. So now, due to the result of Sharma and Venkateramana, we have that the number of generators of gamma is bounded by the number of generators of the profinite completion of gamma plus 3, because the number of generators of gamma hat bounds the number of generators of all finite quotients, and in particular this gamma mod delta that we have. So from now on we're going to bound d of gamma hat. The second important ingredient is what's called the congruent subgroup property. So we saw these subgroup gamma m in SL3Z, and we call these principal congruent subgroups. And we say that a group is a congruent subgroup if it contains some principal congruent subgroup. And the question is, are all finite index subgroup congruent subgroups? So Sir conjectured that they are, or more precisely, every gamma contains a finite index subgroup which satisfies the congruent subgroup property. And in 76, Raghunathan showed that this is indeed the case for all non-uniform lattices. But many cases are also known for co-compact lattices. And now let's see how we combine these two ingredients. So if all finite index subgroups are congruent subgroups, then these quotients are of the form, for example, SLNFP, which are groups that we understand quite well. And we have a lot of theory to work with. To be a little more precise, by what's called strong approximation, if gamma is G of O for the ring of integers, then we can look at the congruence completion of gamma, which is the inverse limit of taking all the congruence quotients of G, and this is isomorphic to G of the profinite completion of O. So this is the congruence completion of gamma. It is again profinite, and it has a very convenient adelic structure, which comes from the ring. And the congruent subgroup property basically tells us that the profinite completion is isomorphic to the congruence completion, or G of the profinite completion of the ring of integers. So for example, the profinite completion of SLN Z is isomorphic to SLN of the profinite completion of Z, which you might know as the product of all ZP, where ZP is the p-adic integers. This is isomorphic to the product of all of these SLN ZP for all primes. But SLN ZP are groups that we have the theory of p-adic analytic groups at hand. In particular, they contain a finite index subgroup, the first congruent subgroup, which is called a uniform pro-p group, or sometimes powerful pro-p group. And they have the following very nice property. If we define the subgroup rank of a profinite group G to be the supremum over D of H over all closed subgroup of G, so we're looking at the supremum of all the ranks of all the subgroups inside G, then a uniform group has finite rank, and in fact the rank is equal to the dimension of G as a p-adic analytic group, which in this case is n squared minus 1. And this is of course very useful since we're exactly looking at different subgroups of such groups. So these uniform bounds on the number of generators of the subgroups helps us to bound the number of generators of our groups. And the proof from then on uses techniques of Dana, Lubotzky, and Lubotzky, which heavily rely on what's called the Prasad's volume formula. So Prasad showed how the volume of these arithmetic locally symmetric spaces, or the covolume of arithmetic lattices, can be computed using the arithmetic data from the field and from the ring of integers and from the algebraic structure of the ambient group with respect to this field. And this is very powerful for proving things like that. Suppose gamma is a lattice, then it is a finite index subgroup of some maximal lattice. Prasad showed that these maximal lattices are basically principal arithmetic subgroups, which have description which is not very far from what we saw so far. So look at the maximal lattice SLNZ. So this is a maximal lattice, and its profinite completion is isomorphic to its congruence completion, which looks like the product of SLNZP, which are p-adic analytic groups. And now at each place we have this first congruent subgroup, which is a powerful p group, and a finite group above it of the form SLNFP. And now here is a very useful lemma of Dana, Lubotzky, and Lubotzky. If gamma is a general congruent subgroup, it has index L, then it contains a principal congruent subgroups of level M, where M is proportional to the index times the volume of the maximal lattice. Or basically you can think of M as being proportional to the volume of a gamma. So we are in the following situation. We have this gamma which sits between SL and Z and the principal congruent subgroup gamma M, and now we can bound the rank of gamma M and the rank of the quotient, which is a subgroup of SL and Z mod MZ, separately. So the first part, we get that D of gamma M turns out to be bounded uniformly, at least for Chevalier groups. So this is because of the structure of SL and ZP as a p-adic analytic group. And we're left with these finite quotients, but also, quite remarkably, the subgroup rank of SL and FP is also bounded uniformly, and it does not depend on P. So the question now is how many P's participate in SL and Z modulo MZ? The answer is, by the prime number theorem, at most log M over log M. But if you remember, we saw that M was proportional to the volume of gamma, so the number of generators of gamma is proportional to log the volume over log the volume. So what's missing for co-compact lattices? So apart from the congruent subgroup property, which is known for many co-compact lattices as well, the only thing that is missing is the result of Sharma and Venkataramana, which use heavily the fact that non-uniform lattices contain unipotent elements. And without it, these methods don't work. But it will be enough to show a much weaker result, that every co-compact lattice of volume V has a finite index subgroup which is generated by at most log V elements. So this will allow us to use exactly the same techniques by passing to the profinite completion. So if you have any idea how to do that, please let me know. And thank you for watching, and if you have any question, feel free to contact me. Thank you.